Hello everyone. So today we are going to solve 24th August GeeksforGeeks problem, that is count prefix balanced binary strings. This problem difficulty level is easy, but first of all, I don't think this is an easy problem. This should be a medium problem at least. And let's see what the problem is saying is we have given an integer n and we have to find the number of binary strings of length 2 star n, basically 2n, and that contain exactly n ones and n zeros such that every prefix of the string contain at least as many ones as zeros. Since the answer can be very large, so we have to return the modulo with the 10 raised to power 9 plus 7. So first thing is I will try to solve, I am going to solve three approaches in this video. So please be with me till the end of this video. You will understand this problem in very detailed. I'm going to start from the brute level approach, like how we are going to optimize this further and further. Okay. So first thing is let's understand the what is the problem is saying is. So consider we have given n equal to 3. Okay, we have given n equal to 3. So mark these points 1, 2, 3, and we have to make the string of 2n. So consider we have six spaces. Okay, how we will start the problem? So there are two conditions. First thing is exactly n, 1n, basically n ones you need and n zeros you need. Okay, and for each and every prefix, you should have at least as many ones as zeros. Okay, so at least as many ones as zeros. So you have to make sure these two conditions. Consider I'm starting with first place. Forget this everything. Let's start from zero. Okay, I can have only two values, one and zero, because this is a binary string. So consider I'm starting with zeros. Is this fulfilling the condition? Consider this is one prefix. Okay, I have not filled any values here. I'm just starting from here. So this prefix is contained zero ones, but one zero. This cannot be possible, right? Because we must have at least as many ones as zeros. But here there is one zero, there is no one. So we cannot take zero here. So it means we need to take one starting from the one. We cannot zero at the starting point. Okay, let's start from here. Can we put one here? Or there is one more conditions like we can put 2, 4, 5, 6. Starting with one, we can put zero also here. Let's start. Let's see this. Are this fulfilling or not? If I'm standing here, if this is the prefix, okay, this is the prefix. So what will the prefix of this? One and one one. Prefix means every starting from the like index, starting index, you have to write the each and every like substring that you are going to encounter. So one and one one we are encounter till now is it is fulfilling like at least one like at least as many ones as zeros. Yeah, there is no zero, but there can be at least zero ones. So it is fulfilling. Similarly, it is fulfilling. And for the exactly n ones and n zeros, we can put further also, right? We need three ones and three zeros. So we can put the remaining at 3 1 3 zeros. So we are good till now. What about this one, 1 0? So prefix will be one and 1 0. This is fulfilling at least as many ones. You can simply say this condition is if you have number of zeros at x, you should have at least number of ones greater than or equal to x. Simply this condition is you can decode this condition to this thing. If you have 0x, then you should have at least or greater than or equal to x ones. Okay, so in this prefix you will say x is 0, so greater than or equal to x, number of ones are there. In this x is 1, so it means there is also 1, so this is also fulfilling. Consider for the third place. Can I put one here? Can I put zero also? So 1 1 0. I'm only iterating this one condition, so that you will understood everything in detail. So can I put one here? Okay, so what will be the prefix now? 1 1 1 1 1 1. We can put, because x is 0, it is fulfilling. X is 0, it is fulfilling. X is 0, it is fulfilling. So it means we can put. Okay, let's start from this. Let's see this condition first. 1 1 0. So what will the prefix 1 1 1 1 0? Can we put this? Yes. This one, yes. This one, yes. Because x is 1 and count of number of the count of zeros is 1. Number of the count of 1 are 2. So that are greater than or equal to number of count of 0. So it means this is also fulfilling. Okay. Let's start further. Can I put one here? No, I cannot put, right? Because for the n equal to 3, I need exactly three ones, exactly three zeros. We have already put three ones, so we cannot put three uh, again one. So we have to put zero. So in this condition, we have only the remaining possibilities, three ones and three zeros. And for each and every prefix, it is fulfilling the condition. So it is one of the possible case. Let's start this one. Can I put 1 here? Let's see. 1, 1, 0, and the other possibility is putting 0 here. Okay. Let's see this one. 1101. What are the prefix? Prefix will be 1, 1, 1, 1, 0, 1, 1, 0, 1. All are fulfilling conditions. Okay, all are fulfilling conditions, so it is good. 1100. Again, it is fulfilling the condition because number of zeros, number of ones are greater than or equal to number of zeros. So it is also fulfilling. Let's start further. Can I put 1 here? I cannot put 1, right? Because number of ones are 3. That we have fulfilled the condition. Now we have to put the number of zeros only. So the remaining positions will be number of zeros only. Now in this case, number of ones are exactly 3 ones, 3 zeros, and each and every prefix is fulfilling the condition. So this is one example. Now can I put 1 here? I can. Okay, I can. Because if you find every prefix 1 1 1 1 0 1 1 0 0 1 1 0 1, every time you have number of ones greater than or equal to number of zeros. Okay. So the remaining case will be this one only because 3 ones we have already encountered. So it means remaining place will be 0 only. So this is also fulfilled. Coming to this case, 1 0. Okay. So what it is saying is, let's erase this so that we can write. Okay, 1 0. So consider this is 1 0 and we have 4 remaining places 1, 2, 3, 4. Can I put 1 here or I will see 1 0 0 3 remaining places? Can I do this? Yes, number of ones is greater than or equal to number of zeros. I can do that. Can I put again 1 and consider the next case is 1 0 1 0 remaining 2 places? I can because number of ones are greater and what are the remaining possibility? Number of ones are exactly n, so the remaining places will be 0. So this is also one of the possible condition. Now this is the one case. Can I put 1 here? I can because the number of ones will be always greater than or equal to number of zeros. The remaining case will be zeros only. So this we can put. Can we, this is a possible condition? No, because here the prefix, write the prefix 1 1 0 1 0 0. This prefix is valid. This prefix is valid. This is not valid because number of zeros are 2 and number of 1 is 1 only. That is not greater than or equal to number of zeros. So this is not fulfilling. So basically the answer will be 1 2 3 4 5. So these will be the answers 1 2 3 4 5. Okay. So like this, you can understand the problem. What it is saying is the problem basically depicts as you have to, there will be two conditions. Okay. And we have given, and you have to write the exactly n ones, n zeros. You have to write it. And the other condition is for every prefix that you are writing, you have to make sure you are going to write the number of ones greater than or equal to number of zeros that you are encountering. Okay. So this is the part of this. So let's start like how we can solve this in the easily manner. Like as we have approached this problem, we will write the solution. Okay. So consider this we have given and how we will write this is, yeah. So for this, consider we have 6 places. Okay. Again, n equal to 3 and we have to write 2n. So 2n means 6 length we have. So for every case, what we are going to check is we have only checking like what was that condition was exactly n ones and n zeros, and other condition was greater than or equal to 1. So consider I have two variable, ones used and second variable is 0 used. Okay. Guys, I'm highly recommend please be with me. You will understand this problem in very detail. Like I'm going to explain 3 approaches in this. Like this is the first approach, that is the brute force. So consider 1 used and 0 used. Okay. This will tell us till now how many ones you have already used. This will tell us how many zeros you have already used. And consider like we are taking the difference from them and consider this is equal to balance. Okay. So what this balance will tell? Balance will tell at every point of time how many ones you have already used minus how many zeros you have already used. So balance will tell how many extra ones, basically how many extra ones you have encountered till now. Consider what it is saying is 101. Consider this, we have the string. Till this point, what is the balance? Balance is 2 ones you have used, 1 0 you have used. So balance is 1. Okay, balance is 1. This is fine. But consider something you have like this 1 0 1 0 0. Now this, consider in this case balance will be 2 ones you have used. So 2 ones you have used. How many zeros you have used? 3. 2 minus 3 is minus 1. Can this be a valid combination? No, because for this prefix you will take C, you have number of ones less than number of zeros, but you should have number of ones greater than or equal to number of zeros. So this will not valid. So it means, can we say that if balance is less than 0, if balance is that less than 0, it means this is not a valid condition. So balance should be always greater than or equal to 0. Okay, balance is always greater than or equal to 0. And at the last point, can we say that if balance is equal to 0, balance is equal to 0, it means exactly number of ones you have used and number of zeros used are equal, because then in that case balance will be 0. If balance is 0, in that case this is a valid condition. This is a valid condition. So hope you understood the problem. So there will be three conditions. Okay, if balance is less than 0, if balance is greater than or equal to 0, or third point is at index n, what is the balance? If balance is less than 0 at any point, it is a invalid condition because number of zeros are more than number of ones. That is not a acceptable condition. If balance is greater than 0, it could be fine. But at the last index, you have to make sure if balance is 0. If balance is not 0 at last index, it means you have used number of ones more than number of zeros. But you must use number of ones is equals to number of zeros. So in that case, balance must be 0 at index n. So in the similar fashion, I will write the Java code. And if you are comfortable with Java, you can refer this. Otherwise, you can take like reference of this code. What I'm trying to say here is if n is equals to 1, okay, let's consider this case also. If n is equals to 1, so it means 2n we have to make. There is only one condition, that is 1 0, because 0 from 0 we cannot start. 0 we cannot start. There cannot be any possible condition. And 1 we need to start. And the remaining position should be 0 because exactly number of ones and zeros are equal. So I'm just simply written this case as a as extra handling base case. And the for the further ones, I'm creating one function. What is function is taking care of 2 star n. Like what is the length we are expecting, index from which index we are starting, and what is the balance once used minus 0 used. Okay. So consider this one only. This is the base case. If index is equals to n, it means I am reached at the last, because this is 0, this is 1, this is 2, this is 3, this is 4, this is 5. So if I reached at the last point, it means balance must be 0 to coming up to the solution. If balance is 0, it means I have found out one solution. If balance is not 0, I'm simply returning 0. It means we have not encountered any solution yet. If balance is less than 0 at any point of time, either index is 0, 1, 2, any index. For any index, if balance is less than 0, it means we are going to return 0. There is no solution for this because you have used number of zeros more than number of ones. Okay. But the third case is if these both conditions are fulfilled, it means you are not reached at the last index and your balance is also greater than or equal to 0. So you have two possibility. Either you will take the number of, either you will pin the number of 1 at that particular index, or either you will pin the 0 at that particular index. If you are making at 1, okay, consider this thing as like this. Yeah. Consider like this. It is you have given number of, consider number of balances 1 0, and what you are going to put here. You have two possibility, right? As we have seen in the example of n equal to 3, we are going to put every time n equal like this position with 1 or 0, and we are now going to check is this fulfilling or not. After putting 1 or 0, is this fulfilling or not? So it means it is fulfilling, then we are going to take the further solutions. If it is not, then we are like at that time we are going to return the finally 0, because this is not going to be give any solution further. So like this only, if I'm going to reach the index plus 1 and I'm taking the balance plus 1, it means whatever the balance I have encountered, if I'm adding 1, it means it will increase my balance by 1. And if I'm adding 0, it means it will decrease my balance by 1. So like this, I'm going to, and if you try to submit this problem, this is a brute force because for every time, for every index you are checking, so it is a exponential time complexity. And only 6 out of 1,000 cases will pass. Let's do the optimization here. What optimization you can do? For any particular point, you have two conditions. So it means we can do optimization with dynamic programming, right? It means there are overlapping problems. So to reduce them overlapping problems, we can use the dynamic programming. Okay, so for dynamic programming, I wrote the code. You don't have to do anything. It's just I'm taking the dynamic programming. If you don't know dynamic programming, it's just you can consider a 2D array. We are going to store the states that we have already completed and we are going to use them further. Okay. So what is that dynamic? What will be the index? So there are two states changing here. One is the index and one is the balance. These two states are changing. So index can, from where it can go. It can go from 0 to 2 into n. Okay, the length 2 into n that we have to find out. So it means 0 to 2, and I made this as a capital N. So it means n finally we can make. And what about balance? Balance again, it can go to n only because all are ones. Consider all are ones. You have put it. So all are ones. It means you have encountered completely 2 into n. So and I'm initializing it with -1 every value. And then now I'm going to same example only. I'm just adding one more condition. If it is not equal to -1, it means I've already calculated the value for this and I'm going to return it. And if it is not, then I'm just storing the value that I'm going to calculate it. It is the same example. I'm using the modulo because we have to return the modulo. I've not used, I guess, it in the recursion code, but you can use that in the similar fashion. You just have to use this modulo. You can define 10 raised to power 9 plus 7, and you have to do modulo with that. Okay, so if you try to submit this, it will able to solve your around 450 test cases. Yeah, 406. So now you can understood like what is the problem. So here the problem again is like we are doing the calculation again and again for each and every index. So let's do the final optimization. What is the that will be saying. So consider, yeah. So third optimization will be Catalan number. Okay. If you are not hear this term before, or if you don't know how to solve this, we will going to see in this detail, like what is the Catalan number and how you are going to solve this. So this is the famous problem like count prefix balanced binary strings, or you have seen the other problems also like balanced parentheses. Consider this is a balanced parenthesis you have to find out. So for at every time you can have open parenthesis more than the closing parenthesis. You cannot have like this, right? One open parenthesis, two closing parenthesis. This is not a valid combination. This is a can be a valid combination where you have open three parentheses and closes three parentheses. So how to find these all the combinations? Okay, if n equal to 3, you have like this also. Okay, this is also a valid combination. So there can be multiple you there can be a multiple same like this. You can depict as 1 0 and opening with the 1 1 1 0 1 0 0, like as we have seen in the binary strings with n equal to 3. So here the same problem it is saying this is the version of the just saying in the you can say terms are different, like here we have to check in the prefix balance, here you have to check in the parenthesis balance. Okay, but nothing, the problem is same. So what is the problem is saying is you have to how to solve these problems. So the optimized approach is you have to use the Catalan number. You have to find the Catalan number for that particular thing. Okay. So consider n equal to 3 we have given. So we have to find the C3. We have to find the C3. What is the C3? C3 is nothing but, or you can write Cn is equals to 2n Cn divided by n plus 1. Okay. What is C? C is a combinatorial function that we have studied in the mathematics. So what it is saying is 2n factorial divided by n factorial. N factorial, this is nothing but 2n. Cn is 2n factorial, n factorial, and n plus 1 is into n plus 1. Okay. This is nothing but this term. Cn is equals to 2n factorial divided by n factorial, and into n plus 1. Now you can find the 2n factorial easily. You can find the n factorial. You can find the n factorial. You can find the n plus 1 and you can do this. Okay. Let's do the one dry run so that you will understood better what I'm trying to say here is. Consider we have n equal to 3. Okay. N equal to 3. So what will be the C3? Okay. C3. So C3 will be 2n factorial, that is 6 factorial, divided by n factorial, that is 3 factorial, n factorial, that is 3 factorial, into n plus 1, that will be 4. Okay. So what is 6 factorial? 6 factorial is nothing but 6, 5, 4, 3, 2 into 1. This is 6 factorial. 3 factorial is nothing but 3, 2, 1. 3 factorial again is 3, 2, 1. And 4 is 4. So this 3 into 2 will divide this 6. This 3 into 2 will divide this. This 4 will be 4. So what is the remaining one is the 5. So 5 will be your answer. So like this, you can using easily find out with the Catalan number. Okay. But how to calculate this? How you will find the 6 factorial? How you will find the 3 factorial? Or this 3 factorial? This is just n plus 1. So this we can easily find out. Okay. Let's see this one also. So consider uh, I am going to create one. Consider I have a factorial table. Okay. This is another variant, like how you find the factorial of a big numbers or numbers. That is another part, but you will understand in this video if you don't know. So because factorial of 0 is 1 always. Okay, 0, 1, 2, 3. Consider we have n equal to 3. Same example. Okay, 0, 1, 2, 3. What is the factorial of 1? Factorial of number is like whatever the number you have encountered, factorial of n minus 1 into n. Okay, this is n into n minus 1 factorial. So factorial of 1 is also 1. Factorial of 2 is n minus 1 factorial, that is 1, and into me 2. So that is 2. Factorial of 3 is factorial of n minus 1, that is 2. 2 into 3 is 6. So basically, this will tell you what is the factorial of every number. Okay, this we are going to store in the consider fact table so that we can use the particular previous factorial that we have calculated to calculate the further also. You don't need this complete array also, because we only need to calculate factorial of any number. Like we can use with the factorial of n minus 1. So you can store it in a variable also. That is the optimization with the space, so that we can use. But the main line, the baseline approach is just like you have to create a factorial, like you have to maintain some states so that you can know for any particular number what is the factorial of the previous number, and you using that you can find out the easily the factorial of that particular number. Okay, so I've written the Java code for this. I'm going to explain how it will like how you can find the Catalan number and what are the important points for that. Okay, so consider this is a factorial. I have created one function, sorry, one array that is 2 into n plus 1. Now initializing it with 1 because factorial of 0 is always 1, and I am just doing the factorial of I equal to I minus 1. But you can also, as I told, you can also use the single variable. You don't need array for to calculate this because we only need the I minus 1 variable value, not the I minus 2 or I minus 3. Now the point is, okay, now the important logic for this is, now this is the Catalan number 2n factorial, n factorial, n factorial, and n plus 1. If you are calculating 2n factorial and if you are calculating n factorial, you cannot divide them directly, right? If you are dividing them, it will give you the unexpected result because we have to divide the modulo of there. Okay, 2n factorial could be a very large number and n factorial could be a very large number. We have to divide their modulo, and we cannot divide their modulo directly. We cannot do like 2n modulo m directly, n factorial m. This is not work. Okay, so how we can do that? So in place of that, can we write this like in basic mathematics? We have seen if we taking the denominator to the numerator, we are doing the inverse of them. Okay, so can we write this modulo of inverse of mod modulo inverse of n factorial? We can do that into modulo inverse again of n factorial. We can do that. Okay, and into modulo inverse. I hope you, I know you are not understanding my writing, but try to be with me. So modulo inverse of n plus 1. Okay, so this we can write 2n factorial into modulo inverse of n factorial into modulo inverse of n factorial into mod of n modulo inverse of n plus 1. This we can tell. So how, what is the meaning of modulo inverse? Modulo inverse is nothing but that we are taking the denominator, we are making it as a numerator to multiplying with it. Multiplying you can do with the modulo, but divide you cannot do with the modulo. Okay, so this is the basic thing that you can see. Now go with the next thing is how you do the modulo inverse. Okay, how do you do the module? Consider you have, you need to find the modulo inverse. And what is the meaning of this modulo inverse? How you find out? Consider if you want to know, go into this mathematics, you can continue, or if you don't know, I will you can skip this part and we are going to see the code like how it will look like. But better if you understood this modulo of inverse. Like consider you have given this variable a into x, and you have to find out 1. This is a famous mathematical equation that you have to consider, and you have some mod m. This x will be called as modulo inverse of a mod m. Okay, this x will be called as a modulo inverse because we are doing the same thing right here. Because x, if I'm multiplying a with x, it will give me 1 that I need. Okay, that I need. So how we'll do that? How we'll consider a is 3 and m is considered uh, 15. Okay, consider m is 7. Okay, this example 3x, and we have to find out m modulus of 7. What will be the value of x? Can x be 1? No, because if x is 1, then 3 modulo of 7 is not equal to 1, right? X is 2, no, 6 modulo 7 is not equal to 1. 9 modulo 7 is not equal to 1. 3, 4, 12. 12 modulo 7 is not equal to 1. 3, 5, 15. 15 modulo 7 is 1. So it means x can be fine. So we could say, we can easily say 3 minus 1 inverse of 3 is equivalent to 5. So if anyhow we have to do 3 divided by 3 modulo of m. If this is a problem statement, easily problem statement is 3 modulo of m divided by 3 modulo of m. We cannot do direct division. So what we can write this is 3 into 3 inverse of 3 modulo m. Okay. And we can easily say 3 into, what is the 3 inverse? 3 inverse is a 5. So 5 and modulo inverse is 7. So 50 modulo 7 is 1. So we can easily say like this is the how you can find out the modulo inverse of this. Okay. So now hope you understood what is the meaning of modulo inverse and how you are going to find out. Okay. So next part is Fermat theorem is coming into the picture. If you don't know, or if you, I'm not also going to the very much detail. If you want to know into detail of the Fermat theorem, you can check online. There can be many tutorials or wiki. Yeah, you can refer them. But the main point here is Fermat theorem is saying a p minus 1 mod, I guess, m equal to 1. Okay. Mod p, sorry, where p is the prime number. So you have to write the equation in the same manner, and I'm going to use that particular thing only. So consider the same thing. Numerator we have find out that is 2n factorial. Denominator we have find out that is n factorial, and n factorial I'm doing this thing, and combination will be, so numerator divided by denominator we have to do, but this is the modulo operation that we cannot do directly. So what I'm doing is modulo inverse of denominator I'm calculating. And finally, what will be my Catalan number will be numerator into combination, so that it will be modulo inverse of n plus 1. Okay. Because, okay, this is the combination we have calculated, and combination into my modulo inverse of n plus 1. So that we have already calculated. Okay. So hope you understood this problem. It is nothing but 2n factorial into modulo inverse of n factorial into n factorial into modulo inverse of n plus 1. And finally, we are going to return this particular Catalan number. What is the modulo inverse? Modulo inverse is just nothing but power of value of mod minus 2. Why mod minus 2? Because this will be resultant into the prime number. And using this Fermat theorem, this is the Fermat theorem example. Using this Fermat theorem, we need to find out this modulo inverse. Okay. Because here what you are doing here is x will, you need to find out, a you have given, m you have given, x you need to find out. One possibility is you can go with x equals to 1 2 3 4 5 6, and what could be the resultant number. Other thing is, using Fermat theorem you can easily find out what will be the x. So using that we are calculating this is the code that I took from online. So if you are okay with that, you can go with that, and if you have any doubt, we will discuss it more. So hope you understood the problem, and if you try to submit it, you will submit with all the test cases. And this is the famous nth Catalan number use case. So if you like, and please learn something new, please subscribe my channel. It would be very helpful to keep continue and to keep motivating. Thank you, everyone.